Welcome dear students, we are on the CEC Gurukul lecture and we are in the series of the quantum technology. Today we will discuss one of the most important topic in the quantum technology is the quantum materials. Yes, quantum materials which is the second quantum revolution. So quantum revolution is about controlling individual quantum system to take these rules and use them to develop the new technologies. So first quantum revolution was atomic and subatomic physics as the new principle governing the physical reality. So second quantum revolution is about the controlling the individual quantum system. So to take these rules and use them to develop the new technology. First, just to discuss about the atomic and subatomic physics and new principle, and second is the controlling the individual quantum system. Just this use for development of the new technology. Example of outcome that could deliver the quantum technology in the coming decades include the knowledge devices and the applications which related to the quantum information technology, quantum electrochemical system, coherent quantum electronics, quantum optics, condensed matter technology and so on. So, if we have the quote about the Feynman, then the nature isn't classical, damn it, and if you want to make a simulation of nature, you had better make it quantum mechanical. And by golly, it's the wonderful problem because it doesn't look so easy. So what I want to talk about is the problem of manipulating and controlling things on a small scale that has been defined by the Feynman. Means problem of manipulating and controlling the things on a small scale. So why cannot we write the entire 24 volumes of the encyclopedia about the same topic? So from nano to quantum. First we come from classical to quantum, quantum to nano, now nano to quantum. So technology allows us to organize and control the components of a complex system governed by the laws of quantum physics instead of exploiting classical physics as in conventional technology. Means we take the classical technology, classical physics as well as, but this technology allows us to organize and control the components, to just manipulate the component, manipulate the devices, manipulate the materials. So two essential drivers in the quantum technology is the miniaturization, or we can say it is a manipulation. Miniaturization as the dominant trend in the last decades to build the devices on a smaller and smaller scale, and ultimately this will deliver the devices at a length scales of the nanometer and the action scale approaching the Planck's constant. So at that point design must be based upon the quantum principle. Means when we talk about the nanomaterial, then there we are having the quantum confinement that will be used for defining the material dimensions as well as the change the property of the material or take it up to the nano scale or the smaller scale. So principle of quantum mechanics is another point. The promise of vastly improved performances over what can be achieved within a classical framework. So quantum principle goals to deliver the useful devices and processes that are based upon the quantum principle. So quantization or the quantum size effect allowed energies of a tightly confined system of particle are restricted to a discrete set. So in this case, uncertainty principle for every perfectly specified quantum state, there is always at least one measurement, the results of which are completely certain, and simultaneously at least one measurement for which the results are largely random. So, quantum superposition in this case, if an event can be realized in the two or more indistinguishable ways, the state of the system is a superposition of each way simultaneously, and that will give the efficient result. Another is the tunneling, which is the ability of the particle to be found in the spatial region from which classical mechanics would exclude it. Another important point in the quantum is the entanglement, which is the superposition principle applied to certain non-local correlation. We are not talking about the relation between the same system, but we are talking about the relation with the other system also. So, if a correlations can be realized in the two or more indistinguishable ways, the state of the system is a superposition of all such correlated all such correlations simultaneously. Another point in the quantum is the decoherence. Decoherence, what depends on the quantum superposition. When an attempt is made to distinguish previously indistinguishable ways as an event can be realized. So, again from indistinguishable to distinguishable, we use the decoherence. So, it renders superposition of probability amplitude into superposition of the classical probabilities. So, decoherence has no analog in the classical physics. In case of the quantum material, what is a quantum material? Which are a particularly crucial in the field of quantum computation. So, quantum material, numerous scientists believe that quantum materials hold the potential to bring about a revolution in various domains, including highly efficient and low data communication, data storage, energy harvesting, semiconductor, supercapacitor, and the artificial intelligence nowadays. In the future, AI, artificial intelligence, will play a vital role in performing and analyzing the numerous calculations like human brain network. So, to train an artificial brain network, artificial synapses should match the biological data processing characteristics which show dynamic behavior towards the signal response. So, now this quantum material exhibit emerging phenomena governed by the quantum confinement, strong electronic correlation, topology, and the symmetry, making them exceptional material. So, if we talk about the application of the quantum material, it is used in the various field like electronic correlation, like in the electronic circuit, like in the data processing, like in the various field of the industry as well as the research. So, quantum material exhibit the emerging phenomena governed by the quantum confinement, strong electronic correlation, topology, and symmetric, which making them extraordinary or the exceptional material. Quantum materials attracted the research community due to their highly controllable electronic structures and non-linear performances. If we talk about the material, it is in the control manner as well as in the manipulation manner. It can just provide the various electronic applications. Hence, quantum material are a developing area for intelligent society. So, a material whose properties cannot be fully described by the classical behavior of the material and whose properties originate from the novel quantum effect are described as a quantum material, as by the law in 2020 and the Summit in 27. Like the material which have the properties as in the terms of the quantum effect. So, material which have the quantum effect is known as the quantum material. So, in classical material, the physical performances of the material can be explained by the particle interaction. For example, ion motion can be classically explained by the electrostatic interactions. However, the quantum mechanics approach can only provide a complete explanation, as a classical theory cannot explain many effects that arise in the quantum material. So, in the quantum material, we use the quantum mechanics, quantum physics, quantum effects to define and to make it the extraordinary material. So, such a quantum fluctuations and the spin entanglement make this quantum material in the use of the quantum computing and in the other area of the quantum technology. Complicated electronic states in the quantum materials originates from the interaction of the degree of freedom. So, that has been defined in 2017, which defined the degree of freedom and the spin interaction. Like there is a quantum material originate from the interaction of the degree of freedom, in which degree of freedom and the spin, in which we have a lattice, charge, orbital and the spin. So, the discovery of the high temperature superconductivity in the copper oxide initiated a significant expansion in the quantum material research. As we talk about the quantum computers, superconductivity is play a better role in the quantum technology. So, quantum material that explain for the superconductivity. So, the macroscopic quantum phenomena could exist beyond the extreme conditions that has been defined in 1986, that we define the superconductivity. So, quantum material contain novel entanglement or topological properties. What is this entanglement or the topological properties? That is the materials with entanglement beyond the requirement of Fermi statistics and with topological responses, like phenomena like quantized vortices in the superconductors provide evidence the topological nature of the quantum wave functions is described by the quantized vortices in the superconductors, that has been defined in the 2012. Now, these vortices arises due to the necessity of the well defined phase in the superconducting condensate with the phases coupling the magnetic flux governed by the gauge invariance. So, topological invariant such as integer winding number indicating the phase winding around vortices. So, remains fixed under the smooth system, changes the impacting various material beyond the superconductors and facilitating phenomena like dissipation, less transport, and these are used, and the unique quasi-particle excitation. Secondly, the non-local entanglement inherent in the specific quantum state has been emphasized notably in experiments displaying teleportation with widely separated photons, that has been defined in the 2021. non-local entanglement, which highlights the interconnectedness of the quantum state. Even within the large system of the electrons, offers us a new frontier for technological advancement and the fundamental physics. So, entanglement, interconnectedness of the quantum states, that is the entanglement. So, entanglement happens in even simple material like metals, where the wave functions of many electrons become very closely linked because electrons are fermionic. So, understanding these quantum phenomena is a specific pursuit and a pathway to practical applications and innovation. For example, if quantum material include the hydrogen sulfide and transitioning from a foul smelling gas to a superconductor with records setting the transition temperature exceeding 200 Kelvin under the high pressure. So, that has been defined in 2015. So, where the entanglement of the electronic and nuclear spins at defect centers enables the long lasting quantum coherence even at room temperature, promising prospects for the quantum technology. What is a brief history research breakthrough in the quantum research? First, start from the 1980 quantum Hall physics, quantum topology, that define the high temperature and high TC superconductivity, that is a strong correlation, that defined in 1980. So, that is a back history from where the quantum generated. So, in 1990 topological early phase, that is the new particles factorization, and here that is a nanoscale physics in 1990. Present topological insulators, spintronics and the multitronics. So, these are the various cold atom advances, spectroscopy, quantum simulators and the nano devices are used, devices using the quantum material presently. And the future, if we talk about the quantum computation and the cryptography, topological electronics, next is about from temperature, superconductivity and motronics. What is a unique property of the quantum materials? As it is an extraordinary material and it is the very manipulated material. So, what are the unique properties of the quantum material that will make it the different from the classical material? So, quantum material having the various properties like interaction of the fundamental degree of freedom, lattice, charge orbital and the spin result in the complex electronic state on the atomic scale. So, fundamental properties of the quantum materials are the quantum confinement, second is the strong electronic correlations, third is the topology and fourth is the symmetry. By keeping in mind, then we just develop the quantum material in the research purposes or in the technology upgradation. So, quantum confinement, strong electronic correlation, topology and the symmetry. So, the properties and the significance, the quantum materials exhibit the properties that are of the profound scientific interest and the practical importance. So, what are the properties and the significance of these properties? First is the quantum entanglement. So, a phenomena where the particles becomes interconnected, entanglement where the particles are interconnected such that the state of one particle instantly influences the state of another particle regardless of the distance between them. So, this is the quantum entanglement. Next is the topological protection. Certain quantum states in the materials are protected by the materials topology making. Like some states will be the intact, it will be protected by the materials topology making whenever we are manipulating, but some of the topological state or the quantum state in the materials are protected. Them resistant, making them resistance to the external disturbances. So, external disturbances will not affect the topology of the material. Another is the superconductivity, the ability to conduct electricity without resistance, leading to highly efficient energy. Another is the transmission, and then is the magnetoresistance. So, a property where a material electrical resistance changes in response to an applied magnetic field, useful in sensors and memory devices. So, the significance of these properties lies in their potential application in the various technologies. For instance, topological insulators could be used in quantum computing, as they provide the stable qubits, the fundamental units of the quantum information. So, one of the example is the topological insulators that is used in the quantum computing, which provide the stable qubits, and that is a unit of the quantum information. Similarly, the superconductors are essential for developing lossless power transmission lines and the powerful. So, powerful magnets used in the MRI machine and the particle accelerators. So, they are the various potential application in terms of the quantum confinement, as size dependent electronic properties can be changed by using the quantum confinement, discrete energy levels due to the confinement, enhancement or enhanced quantum effect due to the quantum confinement, increased band gap with decreasing the size, strongly the size dependent optical properties, moreover the potentials for the tailored optoelectronic devices. Another potential application for the strong electronic correlation, emergence or the novel electronic states, highly correlated behavioral among the electrons, Mott insulating behavior, superconductivity, emergent phenomena like charge ordering or the spin fluctuations, then difficulty in describing with the conventional theories. Another is the topology and the symmetry, that is a non-trivial band structure, robust surface state, insensitivity to local perturbation, unique electronic properties, topological protection against defects and disorders, that will be under the topology and the symmetry. Analogous Hall conductance, where we are having a quantized conductance, we use symmetric protected topological phase, symmetry enriched phase. So, these are the three potential applications for the quantum material. We will discuss one by one, in which first we define the quantum confinement. As a quantum confinement we have discussed in the quantum technology, is in the nanotechnology, where we constrained the motion of the electrons in the one direction, or in the two direction, or in the three direction. So, that is the quantum confinement. So, it is a fundamental phenomena in the nanoscale material, particularly semiconductors and the other confined system. So, it refers to the effect of restricting the motion of electrons and other quantum particle within a region smaller than their characteristics wavelength. So, we use the quantum mechanics to describe particles like electrons as discrete particles and the wave with associated wavelength. So, quantum confinement significantly affects the absorption and emission of the light in the nanoscale material. So, as the energy levels are quantized, the energy difference between the electronic transitions becomes more significant, resulting in more energetic absorption and emission peaks. So, this can lead to enhance the fluorescence, luminescence and the color tunability of the nanoscale materials, which have application in displays, lasers and biological imaging. So, in the bulk materials, the conductivity is mainly determined by the concentration of the free charge carriers, electron and holes, but in the quantum confined system, the discrete energy levels create an energy gap between the highest occupied and the lowest occupied state. So, this can hinder the movement of the charge carriers and reduce the conductivity. However, the quantum tunneling becomes a more prominent at specific energy levels, allowing carriers to pass through the energy barriers and leading to the exciting conductivity behavior. So, quantum tunneling is a phenomena in which particles can penetrate a potential energy barrier that is higher than that of the particle's total energy. By applying the boundary condition, the quantum tunneling is important in many physical operations of the semiconductor devices like tunnel diode and scanning tunneling microscopes, that is based upon the quantum tunneling phenomena. So, a particle's de Broglie wavelength, if it is having lambda and inversely proportional to the momentum p. So, as the size of the confined region become comparable to the smaller than that of the de Broglie wavelength of the particle, their wave like behavior becomes significant. So, in bulk material electrons have continuous energy bands due to the large number of atoms. But in nanoscale material, the confined dimensions impose boundary condition that limit electrons' possible standing wave patterns orbit, and this leads to the quantization of the energy level, where only the specific energy values are allowed. So, the energy levels becomes discrete and resembling the runs of the ladder and rather than the continuous slope. So, the band gap of the material is the energy difference between the highest energy electron in the valence band and the lowest energy electron in the conduction band. So, like that in the nanoscale structure, especially semiconductor nanoparticles or the quantum dots, the band gap increases with the decreasing the particle size due to the quantum confinement. This means that the quantum transitions responsible for optical properties occur at higher energy than in the bulk material. So, finally, we will continue this lecture in the next domain. So, now how we define the quantum confinement, tunneling effect, moreover how we define the strong electronic correlation, then the topology we will define, then in this manner we will continue this lecture. Thank you very much.